Welcome back to my channel. So in this session we're going to be discussing about a derivation on energy density using Einstein coefficient. So you know that in a previous session we have discussed about what do you mean by interaction of light with the matter. So whenever interaction is happening, three interaction will be happening. One is induced absorption, another one is spontaneous emission, and the third one is stimulated emission. If these three happens in the same stream, so then the production of laser will be happening. So what is the energy of that particular laser will be derived by using the following expression. So first we will be finding the rate of induced absorption, rate of spontaneous emission, rate of stimulated emission. So let us consider the energy density equation by considering two energy level where E1 is called as a ground state and E2 is called as the excited state. The number of atom which is present inside the energy level E1 is taken as N1 and the number of atoms which are present in the excited state, that is E2 state, is taken as N2. This is the number of atoms at E1 at E2. So what is induced absorption? Normally if I provide a energy, so we will be taking it as a E mu. So E mu is called as energy density formula. So the energy density, this is the energy which we need to find a derivation by using the phenomena what is happening. So once the energy E mu is provided in any mode of thermal or photon, or it might be electric. So the atoms will be going from ground state to excited state. So it will be consuming the energy E mu, which is directly proportional, and it will be having the atoms which will be moving from ground state to excited state is N1. So if I write this phenomena in this form, that rate of induced absorption means how much atoms has been gone per unit cross sectional area or per unit second will be defined as, it will be always proportional to E mu, that is energy density, and which is the atom which is going, the atom will be going, N1 atoms will be going for the excited state. So the N1 atom, so directly proportional. If I want to remove this proportionality symbol, so I will be adding a constant. The constant will be given as B12. So what is the indication of 1 2? 1 2 will be indicating the direction. The atoms are moving from ground state 1 to 2. That is the indication of the direction. So E mu N1, take it as equation number 1. So what do you mean by B12? This is a Einstein's coefficient of induced absorption. So that is the constant which is given by the Einstein for this particular stream. Similarly, you know that after 10 to the power of minus 8 seconds, the whatever the atoms which has been gone for the excited state, they should come back for the ground state by liberating the energy. Here there is no absorption of energy will be taken place. So it is directly proportional, no energy involved, so that's why E mu will be not used, and the atoms which is coming for the ground state is N2 atoms. So here directly N2 atom will be involved. If I want to remove the proportionality symbol, so I will be introducing a constant, that is A21. So 21 indicates the atoms are moving from excited state to the ground state. So since the emission and the absorption what is happening here is totally different, that's why A21 will be taken as a different constant, N2 will be taken as equation number 2. So what is A21? It indicates Einstein coefficient of spontaneous emission. Similarly, there is a third process which will be happening for the atoms which has been already excited. So for this atom, I will be providing one more extra energy, that is E mu. Means that process has been not completed. So what is happening? The atoms which are involving for the stimulated emission is the atoms which has been excited. and the energy will be provided E mu, that is the extra energy. So it is directly proportional to the extra energy provided in the excited state, and the extra energy will be provided for the atoms which are in the N2 level, that is excited state. So if I want to remove this proportionality constant, since the process has been not completed, so that's why I will be taking the constant as B2, and this is also emission. Emission will be taken place means the atom should be coming from the direction of 2 to 1. So that's why it will be taken as 2 to 1 E mu and N2. Take it as equation number 3, where B21 will be called as Einstein coefficient of stimulated emission. Now totally we will be having a three equations which will be representing a rate of induced absorption, spontaneous emission and stimulated emission. Now I will be taking a condition at thermal equilibrium. So at a thermal equilibrium, what will be happening? Rate of absorption so will be always equal to rate of emission. So normally this will be happening. So since there is a absorption also taken place in our equation as well as the emission also taken place. So we'll be rearranging this one in such a way that rate of induced absorption, that is the one absorption which we have, absorption will be equal to, since we have a 2 emission, so we will be taking a sum of this one, rate of spontaneous emission plus rate of stimulated emission. So we will be rearranging the equation according to the general equation, that is at a thermal equilibrium. So take it as equation number 4. Now apply equation 1, 2 and 3 in equation number 4. Just apply this value in the equation number 4. So what will be happening? So you know that rate of induced absorption, what is the value? B12 E mu and N1. So will be equal to rate of spontaneous emission. This is the spontaneous emission where A21 and N2, that is the equation, plus rate of stimulated emission. The equation which is representing is B21 E mu N2. So we will be writing the equation according to the requirement. So next what will be happening, just I want a energy density formula here. So that's why I will be shifting all for the right hand side. It will be B12 E mu N1 minus B21 E mu N2 is equal to A21 N2. Just we will be shifting the equation. Now I will be taking energy density E mu as a common term outside, and the equation will be going as B12 N1 minus B21 N2 is equal to A21 N2. Just I will be rearranging the equation according to our equation, and now I want only the equation as energy density. I don't want entire equation, so I will be shifting this bracket term to the denominator. The value will become A21 N2 divided by B12 N1 minus B21 N2. Now the same equation, so since there is a N1 N2 term in the denominator, I will be taking a N2 term in this denominator common, the value will be n2, and since in the first term there is no n2, so what we need to do, we need to divide the number what we have took it as a common minus b21, since there is a n1, so that will be coming as a common term outside, and we will be cancelling n2 n2. Now we will be rewriting the equation which has been already cancelled, and once again what I will be doing, I will be taking one more common. What is the common? So I will be taking b12 outside. b12, it's nothing but the Einstein coefficient for the induced absorption in the denominator, n1 divided by n2 minus b21 divided by b12. Just I will be taking out, right? So as soon as this is taken outside, so you know that b12 is taken outside, and here there is no b12 term, that's why I have divided here. Now by using Boltzmann formula, so what I will be doing, I will be using a Boltzmann formula. What is the Boltzmann formula states? If I want to know the ratio of the atoms which are in the number of atoms in the excited state with respect to number of atoms in the ground state, will be always equal to e to the power of minus of delta E divided by kT. So but in my equation, take it as equation number 5. So what is happening in my equation, there is the value as n1 divided by n2. So if I rearrange this equation, the equation will become as n1 divided by n2 is equal to e to the power of plus. If I rearrange this, it will be going for the denominator, so 1 over e to the power of x can be written as e to the power of x. So the value will become plus delta E divided by kT. Take it as equation number 6. Applying equation 6 in equation 5. So what will be happening? I will be applying n1 divided by n2 value as e to the power of delta E divided by kT. So the energy density formula will become A21 divided by B12, and n1 divided by n2 will be e to the power of delta E divided by kT minus B21 divided by B12. Just I will rearrange this equation. Take it as equation number 7. Now we know the Planck's formula for the energy density already. E mu, already we know for the normal interaction of light, the Planck's has already given a formula for this one. So what we will do, so we will be writing that formula. What is the formula? E mu is equal to 8 pi h mu cube divided by c cube into 1 divided by e to the power of delta E divided by kT minus 1. This is the formula of a energy density which has been given in general for the normal light, for the induced absorption and a spontaneous emission which will be taken place for the light. Now what we will do, we will compare equation 7 and equation 8. We will be comparing this equation. What will be the comparison? Just observe, in the place of the ratio, in the place of A21 divided by B12, what is there? The value is 8 pi h mu cube divided by c cube is there. So this is the comparison. And one more comparison, just observe. So B21 divided by B12, in the place, now in the place of B21 divided by B12, what is there? The value is equated to 1. Now by comparing, I can say that the rate of whatever the coefficient Einstein coefficient of stimulated emission will be equal to Einstein coefficient of induced absorption at a thermal equilibrium. I can equate. So by generalizing the equation, as soon as this is finished, I can easily say that by comparing this one, the energy density for the laser E mu is equal to A divided by B. In spite of writing A21 and B12, because nothing, no term is there extra like in the B value, now I can write it as A by B into e to the power of delta E divided by KT minus 1. So this formula will be representing the energy density formula for laser. So this is the actual derivation. So in the exam point of view, this will be asked for the